Welcome to today's lesson in physics. Today we are continuing with Rutherford model and we are discussing two terms in the alpha scattering experiment, that is impact parameter and distance of closest approach. The figure shows the trajectories of different alpha particles which are approaching a particular nucleus. So the path followed by the alpha particle, it depends on a term called impact parameter. In the picture, we can see one angle marked theta. That angle marked theta is called as the angle of scattering. And we know the angle of scattering is the angle between the direction of initial velocity vector and the direction of scattering. That means after scattering, in what direction it gets deflected, the alpha particle gets deflected. The angle between the two directions is called as the angle of scattering. So here it is marked as theta. And this theta, it depends on a particular term called impact parameter. That impact parameter, it depends or it is defined as the perpendicular distance of the initial velocity vector of the alpha particle from the central line of the nucleus. As you can see here, this is the central line of the nucleus. This is the central line and the initial velocity vector, it is written u. Okay, so that perpendicular distance between the two, that perpendicular distance is called as the impact parameter. So impact parameter is the perpendicular distance of initial velocity vector of the alpha particle from the central line of the nucleus. Now, what is the significance of this term impact parameter? It means that, or it is a measure of the angle of scattering, we can say. If the incoming alpha particle is far away from the central nucleus, or if the impact parameter is large, the angle of scattering will be less. So for large impact parameters, the deflection will be less and the scattering will be less. So that's the importance of impact parameter. Smaller the value of impact parameter, larger will be the angle of scattering. Rutherford introduced a relation between angle of scattering and impact parameter as 1 by 4 pi epsilon 0 ZE square cot theta by 2 divided by EK, where Z is the atomic number of gold nucleus, E is the charge of the electron, theta is the angle of scattering, and EK is the kinetic energy of incoming alpha particle. So EK stands for kinetic energy of the incoming alpha particle. So from the picture you can see that the farthest particle, that means for the particle for which the impact parameter is very large, that particle, it goes undeflected. There is no scattering for such a particle. And for the other particle which is at moderate distance, its deflection is very less. So larger the impact parameter, smaller will be the angle of scattering. Okay, so for large value of B, cot theta by 2 is large. Take care, it is cot theta by 2 and the scattering angle theta is small. That means alpha particles traveling far away from the nucleus, they suffer small deflection. And for small value of B, cot theta by 2 also is small and theta, the scattering angle, is large. That means alpha particles traveling close to the nucleus suffer large deflection. And here comes a special case for B equal to 0. B equal to 0 means there is a head-on collision. In such a case, alpha particles, it is directed towards the center of the nucleus and we can say that theta equal to 180 degree. That means such a alpha particle will retrace the path. Okay, so in that case, theta equal to 180 degree. So for B equal to 0, theta equal to 180 degree. and if theta equal to 0, B will be maximum. That means the particle will not be undergoing any deflection in such a case. Now let's discuss what is meant by distance of closest approach. As we discussed in the case of impact parameter, the last case we discussed in the case of head-on collision. In such a case, when an alpha particle moves directly towards the nucleus, we can say that there will be repulsive force between the alpha particle and the positively charged nucleus, because the nucleus consists of positive charges. So there is repulsion. Because of this repulsion, the velocity and kinetic energy of this incoming alpha particle, it decreases continuously, and at a particular distance from the nucleus, this kinetic energy becomes zero and the alpha particle, it comes to rest. That means momentarily the alpha particle will stop, and because of that repulsion, this alpha particle start retracing its path. That means it goes back. At that point, that means at the position when it just retraces the path, its kinetic energy is completely converted to electrostatic potential energy. That is why it's coming to rest. Its kinetic energy is zero, but energy cannot be destroyed. No, it can be transformed from one form to another. So at that point where its kinetic energy is becoming zero, at that point only it is coming to rest. And what has happened to its kinetic energy? Its kinetic energy has been fully transformed to electrostatic potential energy. And that distance at which this alpha particle is coming to rest and it starts retracing its path, that distance is called as distance of closest approach. And at the distance of closest approach, we can equate the kinetic energy of the incoming alpha particle. That means it is completely transformed. So kinetic energy of the incoming alpha particle, it is equal to the electrostatic potential energy at the distance of closest approach. So if we denote distance of closest approach by the letter D, the expression for distance, this electrostatic potential energy, it becomes 1 by 4 pi epsilon 0 Zd into 2E divided by E divided by D. We know the expression for electrostatic potential energy, 1 by 4 pi epsilon 0 Q1 Q2 by R12. So here Q1 is the gold nucleus, its charge is Ze. Here E is the charge of the proton. Okay, we know that both the proton and electron, they have same amount of charge. Proton is having positive charge and electron is having negative charge. Okay, so that is why it's written Ze and into 2E. 2E is the charge of incoming alpha particle. And D is that R12, we say the distance between gold nucleus and the alpha particle. So rearranging that equation, we have the distance of closest approach as 1 by 4 pi epsilon 0 into Zd into 2E divided by half mv square. Okay, and this distance, when we calculate in different cases, we will get it of the order 10 raised to minus 14 meter. Now we will discuss a problem, that is example 12.2. 12.1 you can just read, that is very simple. In a Geiger-Marsden experiment, what is the distance of closest approach to the nucleus of a 7.7 million electron volt alpha particle before it comes momentarily to rest and reverses its direction? So in short, what it is asked is to find the distance of closest approach. So the whole process is explained here. You can go through, and we have the expression for distance of closest approach, D equal to 2Ze squared divided by 4 pi epsilon 0 k, where k is the initial kinetic energy of the incoming alpha particle, which is 7.7 million electron volt. Okay, so by substituting, we'll have 2 into z. We have to substitute for z. Z is equal to 79 for gold, and 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. E is 1.6 into 10 raised to minus 19, and K, it is 7.7 million electron volt. We have to convert it into joule. So we have to multiply it with 1.6 into 10 raised to minus 13. Now we will get D as 3.84 into 10 raised to minus 16 Z. Z is 79. So we get it as 3 into 10 raised to minus 14 meter. In Fermi meter, if we are writing 1 Fermi meter is 10 raised to minus 15 meter. So we'll get it as 30 Fermi meter. So that is the distance of closest approach. So only this much for today. Thank you.